10.6 Dalton's Law of Partial Pressures. The total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. In other words, the pressure total is equal to the pressure of gas 1 plus the pressure of gas 2, etc. When you collect gases over water, as depicted here, there's water vapor mixed in with the gas. So not only do you have the gas that you want to be collected, but you also have water molecules that have left the surface of the solution and have also gone into the gas phase. To find only the pressure of the desired gas from your reaction, you must subtract the water vapor of water from the total pressure. Sample exercise 10.10, applying Dalton's law to the partial pressures. A gaseous mixture made from 6 grams of oxygen, 9 grams of methane, is placed into a 15-liter vessel at 0 degrees Celsius. What's the partial pressure of each gas, and what is the total pressure in the vessel? We need to calculate the pressure for 2 different gases in the same volume and at the same temperature. Because each gas behaves independently, we can use the ideal gas equation to calculate the pressure that each would exert if the other were not present. The total pressure, then, is the sum of these 2 partial pressures. First, we must convert the mass of each gas to moles. So we've taken the mass of oxygen and multiplied by a conversion factor to convert grams to moles. We get 0.188 moles of oxygen. And then we're converting 9 grams of methane to moles of methane, again, using the conversion factor to do that. We get 0.563 moles of methane. Once we have moles, we can plug the moles into the ideal gas law. So to get the pressure of the oxygen, they've just rearranged PV equals nRT to P equals nRT over V. You don't have to rearrange the equation to solve this, but that's what they've done here. Plugging in the mole values for the oxygen and the methane into separate equations using the correct ideal gas law constant, and the temperature was given as 0 degrees Celsius or 273 Kelvin. The volume was 15 liters, making sure that all of our units are canceling, and we're left with atmospheres. And we then have 2 pressures, one for oxygen and one for methane, which we then add together and get 1.122 atmospheres. Practice exercise. What is the total pressure exerted by a mixture of 2 grams of hydrogen and 8 grams of nitrogen at 273 Kelvin in a 10-liter vessel? Sample exercise 10.11, relating mole fractions to partial pressures. A study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.5 mole % carbon dioxide, 18 mole % oxygen, and 80.5 mole % argon. Calculate the partial pressure of oxygen in the mixture if the total pressure of the atmosphere is to be 745 torr. If this atmosphere is to be held in a 121-liter space at 295 Kelvin, how many moles of oxygen are needed? We first need to calculate the partial pressure of oxygen, given its mole percentage and the total pressure of the mixture. We need to calculate the number of moles of oxygen in the mixture, given its volume, 121 liters, temperature, 745 torr, and partial pressure from part A. We will calculate the partial pressures using equation 1015. We will then use the pressure of oxygen, volume, and temperature together with the ideal gas equation to calculate the number of moles of oxygen. The mole percent is just the mole fraction times 100. Therefore, the mole fraction of oxygen is 0.180 because they had told us that it was 18 mole % oxygen. We then multiply 0.180 times 745 torr, the total pressure of the atmosphere, and we get the pressure of the oxygen, 134 torr. We then convert the torr to atmospheres, so the pressure of oxygen is 0.176 atmospheres. The volume was 121 liters, and we're trying to find moles of oxygen. We have our gas law constant with the correct units, the temperature as 295 Kelvin. We are then going to solve for moles of oxygen, rearranging PV equals nRT to N equals P times V over RT. We make sure that our units cancel out appropriately, and we're left with 0.879 moles of oxygen. Practice exercise. From data gathered by Voyager 1, scientists have estimated the composition of the atmosphere of Titan, Saturn's largest moon. The total pressure of the surface of Titan is 1,220 torr. The atmosphere consists of 82 mole% nitrogen, 12 mole% argon, and 6 mole% methane. Calculate the partial pressure of each of these gases in Titan's atmosphere. Sample exercise 10.12. Calculating the amount of gas collected over water. A sample of KClO3 is partially decomposed, producing oxygen gas that is collected over water as in figure 10.16. The volume of gas collected is 0.250 liters at 26 degrees Celsius and 765 torr total pressure. How many moles of oxygen are collected and how many grams of KClO3 were decomposed? So we need to calculate the number of moles of oxygen gas in a container that also contains water vapor. If we tabulate the information presented, we will see that the values are given for volume and temperature. To use the ideal gas equation to calculate the unknown moles of oxygen, we also must know the partial pressure of oxygen in the system. We can calculate the partial pressure of oxygen from the total pressure and the vapor pressure of water. The partial pressure of the oxygen gas is the difference between the total pressure, 765 torr, and the partial pressure and the pressure of the water vapor at 26 degrees Celsius. There's tabulated water vapor pressures in Appendix B in your textbook. So if we look up that value, we'll see that at 26 degrees Celsius, the water vapor pressure is 25 torr. We then subtract the water vapor pressure from the total pressure and get the pressure of just the oxygen, 740 torr. We can use the ideal gas equation to calculate the number of moles of oxygen. Now that we know the pressure of just the oxygen, we're converting torr to atmospheres with that conversion factor and then multiplying by the volume in liters and dividing by our ideal gas law constant in the right unit and multiplying that by our temperature in Kelvin, making sure again that all of our units are canceling appropriately. We get that the moles of oxygen is 9.92 times 10 to the negative third. We now need to calculate the number of moles of reactant that decomposed. We can use the number of moles of oxygen formed and the balanced chemical equation to determine the number of moles of KClO3 decomposed, which we can then convert to grams of KClO3. So from equation 1016, we have 2 moles of KClO3 to 3 moles of oxygen. It's a 2-to-3 ratio. The molar mass of KClO3 is 122.6 grams per mole, and then we can convert the moles of oxygen that we found in part A to moles of KClO3 and then to grams. So this is a little bit of stoichiometry. Again, there's your mole ratio, the 2-to-3 ratio from the balanced chemical equation, and then converting moles to grams using the molar mass. So our final answer then for part B is 0.811 grams of KClO3. Practice exercise. Ammonium nitrate, NH4 and O2, decomposes upon heating to form nitrogen gas. When a sample of this compound is decomposed in a test tube, as in figure 1016, 511 milliliters of nitrogen gas is collected over water at 26 degrees Celsius and 745 torr total pressure. How many grams of NH4 and O2, ammonium nitrate, were decomposed?